The promise of AI coding was simple. Dispatch a dozen autonomous agents at once and ship features 12 times faster. But dispatching multiple agents into a shared codebase without constraints scales chaos rather than velocity. Code quality degrades rapidly, and the repository takes systemic damage. This chart compares traditional pull request, or PR, review times against AI batching. A PR is a request for human developers to review and approve new code before it merges into the main project. Parallel generation causes a 91% increase in review time, turning human reviewers into a massive bottleneck. While human reviewers are bogged down, technical debt accumulates. Static analysis warnings, automated checks that flag poor coding practices, rise by 18% per session. Security is sacrificed for raw speed. 45% of this rapidly generated AI code contains active vulnerabilities. High-velocity generation shifts the engineering burden from the editor to the PR queue, forcing developers to spend their time triaging a backlog of broken software. To understand why this happens, we have to look at how a standard shared repository handles these requests. Currently, multiple agents are dispatched simultaneously, with no awareness of the overall system state. In naive batch dispatching, isolated agents blindly attempt to overwrite the exact same shared files at the exact same time. This creates runtime state corruption. The codebase fractures, generating silent merge conflicts that easily bypass a developer's initial scrutiny. Solving this requires abandoning open batch dispatching in favor of a deterministic, constrained execution engine. This engine is built on TRIZ. TRIZ is a problem-solving methodology created by analyzing over 2 million patents to codify universal rules of invention. By applying 6 specific TRIZ principles, we can architect an orchestrator that manages concurrent AI agents without corrupting the repository state. Safe concurrency requires the absolute isolation of tasks. This begins with TRIZ principle number 1, segmentation, which dictates dividing a system into independent parts. Before any tasks are dispatched, the system extracts a strict dependency graph based on file paths. A dependency graph is a map showing how different files in the codebase rely on one another. This ensures agents never share working territories. But static planning has a vulnerability. If a background process or human developer is already modifying a seemingly isolated file, the system is still at risk of corruption. To counter this, we apply TRIZ principle number 10, prior action, which involves performing required changes of an object in advance. The engine runs a pre-flight check before every batch, scanning a real-time conflict ledger to ensure no active agents overlap with the new tasks. By mathematically isolating working directories and verifying file availability through the ledger, the engine prevents structural overlaps from reaching the execution phase. Prevention is only the first layer. We must also examine the internal mechanics of the AI agents themselves. This introduces TRIZ principle number 40, composite materials. We shift the agent from a uniform property to a composite construction. Instead of a single coder prompt, the contracts are structured as multi-persona pipelines. Every agent is forced to simultaneously act as the coder, the tester, and the reviewer. To enforce these personas, the system applies TRIZ principle number 3, local quality. Every agent operates in an isolated sandbox where it must pass a mini quality gate, running its own tests and static analysis on its modified files before reporting completion. Forcing validation directly at the source ensures that bugs are identified and corrected by the agent that wrote them, keeping them out of the human reviewer's queue. Even with strict planning, an autonomous agent can still behave unpredictably and modify a file it was never assigned to touch. Managing this requires TRIZ principle number 18, feedback. When an agent completes its task, it reports the actual files it modified. The conflict ledger, a real-time registry of all file access, instantly cross-references this against the expected list. If an overlap is detected, the run immediately halts. A dead stop protects the code, but the system must recover its momentum without waiting for a manual reset. This brings us to TRIZ principle number 15, dynamicity, allowing system characteristics to change to remain optimal. The engine learns through adaptive batch sizing. When conflicts are detected, it throttles concurrency, dropping to a safe, sequential fallback of one task at a time. The orchestrator operates as an adaptive governor, automatically throttling its own velocity to maintain the integrity of the repository. Viewed as a whole, the TRIZ parallel engine acts as a fully constructed, multi-layered defense mechanism. Prevention and early detection act as the proactive outer shields, parsing dependencies and enforcing local quality gates. Self-healing acts as the intelligent governor within the system, adaptively sizing batches based on real-time feedback. If an irrecoverable conflict breaches those outer layers, the engine relies on Tier 4, explicit rollback. Because each agent operates in its own sandboxed context, a triggered conflict halt automatically aborts all subsequent tasks, and the corrupted commit is blocked from being pushed. This architecture is engineered to fail safe, prioritizing the absolute integrity of the master branch above all else. For the engineer, this architecture practically translates into a specific set of critical interventions when the system triggers a halt. If a parallel dispatch is halted due to a file conflict, the developer uses the command line interface to clear the ledger and reset the parallel session state safely. Within the IDE, the software suite where developers write code, an agent that fails its local quality gate is flagged with a warning icon on the task board. The developer reviews the raw log, fixes the bug directly, and redispatches the task. Concurrency without rigorous state constraint is merely the automation of technical debt. True reliability emerges from systematic, mathematically sound dependency management rather than the raw addition of more agents.